In this video, we're not going to configure alerts, we're going to engineer them. Because most alert misconfiguration doesn't come from not knowing where a setting is. It comes from not understanding how the alerting system actually behaves over time. And if you don't understand that behavior, you end up in one of two situations. You either get noise, or you detect real incidents too late. Neither is acceptable, so let's reset this properly. Most people think alerting works like this. A check fails, an alert fires, it's fast and it's simple. And that is the wrong mental model, because a single failed check is not automatically a meaningful outage. An outage confirmed internally is not automatically something that should wake a human. Those are two separate decisions. Detection is one decision, notification is another, and in StatusCake they are deliberately separated. Every alert in StatusCake follows a pipeline, not a trigger, but a pipeline. First, a scheduled check runs. Second, that check is evaluated against your validation rules, your timeout, your status code, your content matching. If it violates those rules, that individual check fails. Third, confirmation servers run immediately. This is a validation batch. 1 to 3 additional servers rerun the same test. Majority rule decides whether the failure is real. If the majority confirm it, an incident state is created, and that is important. Because at this point, an incident exists, but no human has necessarily been notified yet. Because after incident creation, there's another gate, the notification gate. This is where alert delay and routing logic decide whether to escalate the event to Slack, email, SMS, or anywhere else. So the system isn't fail alert, it's check, validate, confirm, create incident, and notify. That structure is intentional. Let's simplify the separation. Detection answers is something wrong. Notification answers is this important enough to interrupt someone. Those are not the same question. You may want to track short disruptions. You may not want to escalate them. You may want to log every incident. You may only want to wake someone for sustained downtime. That decision happens after detection. And if you treat them as the same thing, you end up configuring everything emotionally. You react to failures instead of engineering signal. Now here's why the confirmation step matters. Because not all failures are equal. A single failure followed by a pass is often noise. Routing, transient latency, a regional hiccup. But consistent failure is signal. The goal of confirmation is not to slow you down. It's to prevent you reacting to a single unstable data point. Monitoring systems that alert on single failures are fast, but they are unstable. Monitoring systems that confirm internally before alerting are slightly slower, but dramatically more reliable. The goal is not maximum speed. The goal is meaningful speed, speed with confidence. Here's the clean mental model to carry forward. Detection determines correctness. Confirmation determines confidence. Notification determines interruption. 3 stages, 3 separate responsibilities. And when you understand them independently, alert noise becomes predictable, not random. Now that we've established the pipeline, we can step into something more precise. Because once you understand the stages, you can begin to predict timing, and alert timing is not mastery. It's the direct result of your configuration. Now we move from structure to timing, because once the pipeline exists, the next question becomes, how long does it take to move through it? Alert timing is not random, it's math. Let's break it down properly. On the screen, you'll see a simplified equation. Time to notify equals check rate plus confirmation time plus alert delay. That's your timing budget. So when someone says, why did it take 4 minutes to alert? The answer is not emotional, it's mechanical. The system runs on schedule. A failure can only be detected when a scheduled check runs. That's your first constraint. Then confirmation happens inside that window. Then optionally, alert delay applies. Each component adds structure to the timeline. If you understand those pieces, you can predict the outcome before an incident ever happens. Check rate determines how often we look. If you check every 60 seconds, the worst case detection time is nearly 60 seconds. If you check every 30 seconds, it's nearly 30 seconds. This doesn't change validation logic. It changes temporal resolution. Think of it like frames per second. Higher frequency gives you finer detection granularity. Lower frequency gives you wider intervals. You are not making monitoring better, you are making it more time sensitive. That's the trade-off. This is where people often misunderstand the system. Confirmation does not mean wait 1 minute, fail again, wait another minute, fail again. No. The confirmation batch runs immediately after the first failure, within the same check window. If majority rule confirms downtime, the incident begins there. You do not need 3 separate minutes to validate it. Validation happens fast. Scheduled checks determine cadence. Confirmation determines confidence. These are different mechanisms. Now we apply alert delay. Alert delay does not change detection speed. It changes interruption timing. An incident can begin at T0, but if you have a 5-minute alert delay, the system waits. If the outage resolves inside that window, no notification is sent. If it persists beyond that window, notification fires. So detection speed and notification speed are not the same thing. And this is where many teams confuse slow alerts with intentional escalation control. Delay is not indecision, it's escalation policy. Now look at 3 example configurations. Fast and sensitive, 30-second checks, no confirmation, no delay, fastest possible alert, highest risk noise. Balanced, 60-second checks, 2 confirmation servers, no delay, slightly slower, much higher confidence. Then we have sustained only. 60-second checks, 2 confirmation servers, 5-minute delay, high confidence, reduced interruption, slower notification. None of these are correct universally. They are correct relative to business impact. So the question remains, when should we use each different setup? Say you have a checkout page. You're going to want to go for fast and high confirmation. A marketing microsite, balanced or sustained only. Monitoring is not about speed alone, it's about signal quality relative to importance. Let's simplify this properly. Check rate defines how often you look. Confirmation defines how certain you must be. Alert delay defines when a human is interrupted. Together, they define your alert timing profile. Monitoring is not reactive, it's engineered. And once you understand the timing model, you stop guessing. Now let's take a step back for a second. Monitoring is not about reacting to every failed check. It's about reacting to meaningful failure. A single failed request is data. A confirmed outage is signal. A notification is escalation. These are 3 different layers of responsibility. And when you understand them separately, alert behavior stops feeling unpredictable. It becomes engineered. Speed without confidence creates noise. Confidence without speed creates delay. Good alerting lives in the balance between the two. And that balance is not universal. It depends on what you're protecting.